Hello, this is Deborah Chung at University at Buffalo discussing about structural self-sensing, which has to do with a structural material, sensing itself without sensor incorporation. And the concept is based on the structure-property relationships with the properties being the electrical properties. And this pertains to multifunctional structural materials, with the material serving both structural and non-structural functions. There's no device involved, so low cost, high durability, no mechanical property loss. Also, design simplification and large functional volume. If one incorporates or embeds a device in a structure, one has to do it while the structure is being fabricated, and subsequent repair might be difficult. In contrast, in self-sensing, there's no device involved. Rather, one measures using certain meters, certain electrical properties of the structural material. This is a disaster in Miami. This building collapsed suddenly. It would have been nice if we had some early warning. And cement is used as a sealant for oil, gas wells and other wells. And if the sealant is not good, we can have an oil spill. So checking the integrity of the seal is very important. We are really talking about real-time monitoring, which is better than occasional monitoring. The structural materials that I'll cover include continuous fiber polymer matrix composites as used for aircraft, and cement matrix composites as used for buildings and highways and so on. The attributes sensed include strain, stress, damage, and temperature. The electrical measurements can involve measuring the resistance, capacitance, or inductance. And I'm going to start with resistance. Continuous carbon fibers are well known for their high modulus of elasticity, high strength, and low density, so they are widely used for lightweight structures. And aircraft increasingly use that, even cars and bicycles and golf clubs and tennis rackets. This is me in 1993 when I invented smart concrete, which contains a little bit of short carbon fiber that modifies the electrical behavior so that the sensing becomes good. Short carbon fibers look like this, and their dispersion in the cement is very important. And it turns out that the addition of silica fume or fine silica particles into the mix helps loosening up the fiber clumps. The conductivity increases with increasing conductive filler content, in this case, short carbon fiber content. When it's above the percolation threshold, you have touching between the filler units, and so it's conductive. And the sensing is best if the composition is near the percolation threshold. And this is the plot of the resistivity versus volume fraction of short carbon fiber, and it does drop by orders of magnitude, and the drop is sharper if you have no sand. Applications involve weighing the trucks as they move, also providing infrastructure to provide sensing for autonomous vehicles. This is weight-based sensing. Also, one can have building intruder detection provided by weight-based sensing and with no camera involved, and structural health monitoring as well. Electrical measurement sounds easy using a meter, but there are many pitfalls. For measuring the resistance, there are two methods, 4-probe method and 2-probe method. Here I'm holding onto a sample and with 4 wires wound around, and this is the 4-probe method. In the 4-probe method, the outer 2 probes are for sending in the current. The inner 2 probes are for measuring the voltage. As a result, there's no current going through the voltage probe, and the measured resistance excludes the contact resistance. However, if one uses the 2-probe method, the measured resistance includes the contact resistance. And if one is trying to find out the effect of stress or heat on on the resistance, it'd be even more troublesome for the two-probe method because both the contact resistance and the specimen resistance may change at the same time. Resistance-based sensing is largely based on piezoresistivity, which refers to the change of the electrical resistivity due to the strain. The severity of this effect is called the gauge factor, which is the fractional change in resistance per unit strain. There are three styles of resistance measurement: volume resistivity for sensing a volume, contact resistivity for sensing an interface, and surface resistance for sensing a surface region. And I'll first talk about the volume resistivity. This is carbon fiber cement under repeated compression. Shown in thin line is the longitudinal strain, and I have an arbitrary progression of strains at different amplitudes of the strain, and the bold line is the resistance, and every time one compresses, the resistance goes down. And I can plot the resistivity versus the strain amplitude and connecting the data points in chronological order. And one sees that it's kind of linear and not much hysteresis. And that's done using the 4-probe method. However, if one uses the 2-probe method instead, it's a mess. This is the same thing, but under tension, a 4-probe method again. And under tension, the resistance increases, just the opposite of compression. And note that is very nicely reversible. However, if one takes away the carbon fiber, there's still an effect, but it's not totally reversible. Also, the magnitude of the effect is much less than the case with carbon fiber. A freeze-thaw damage is a trouble for concrete structures such as pavement. And this is because ice has lower density than water. And we have been able to monitor the freeze-thaw damage in real time by resistance measurement. And in thin line is the temperature going below 0 degrees C to above 0 degrees C. And the thick line is the resistance. And every time it warms up, the resistance goes down. And that is because there are interfaces. And upon increasing the temperature, the chance of the electrons jumping across the interface increases, thereby reducing the resistivity. And note that the baseline resistance incrementally increases in every freeze-thaw cycle, meaning that there is additional incremental damage inflicted at every freeze-thaw cycle. And at the very end of this life, the resistance shoots up, and that shooting up occurs at the coolest point of the last cycle. Now, conventional, and note that this is the plot of the resistivity versus the temperature, and as I said, that's the trend. The higher the temperature, the lower is the resistivity. But note that there's a little glitch that occurs at 0 degrees C. This is the conventional method of freeze-thaw durability evaluation involving residual strength measurement, and that is destructive and involving many specimens, not just one. Another method of temperature measurement involves the thermocouple, two dissimilar materials electrically connected. And we can have cement-based thermocouple, with one material being carbon fiber cement, which is P-type, with positive thermal power, and the other is steel fiber cement, which is N-type with negative thermal power. So one forms a p-n junction, that is the two materials in intimate contact, and it does work. This is the Seebeck voltage versus the temperature difference. Now, the p-n junction is famous in the semiconductor world as a diode. And for the cement-based p-n junction, we don't have a very beautiful diode, but there's some of that characteristic, with the current being more in one direction than the other. Now let me turn to continuous fiber, which is more effective as a reinforcement than the short ones because the fiber matrix interface is never perfect. Let's consider, say, epoxy. And we fabricate the cement, the epoxy matrix composite containing the continuous carbon fiber. And during the fabrication, particularly during the cooling part, the resin contracts, and that results in residual stress that is compressive in the carbon fiber. And one can ascertain that by resistance measurement, by taking a single carbon fiber, embedding that in epoxy, and having the two ends of the fiber stick out to provide ABCD for the 4-probe resistance measurement. And we do this measurement during tension on the single fiber. And indeed, during tension, the resistivity of the single fiber decreases, and it's reversible upon unloading. And this decrease in the resistance is because the tension is canceling out the compressive residual stress in the fiber. And this extends to the behavior of a laminate with continuous carbon fiber in epoxy. At the bottom, it shows the longitudinal volume resistance. It indeed decreases and is quite reversible, just like what we saw in the case of a single fiber. Now, for a continuous fiber laminate, the carbon fiber is conductive, but the matrix, a polymer like epoxy, is not conductive. In spite of that, the through-thickness resistivity is never infinity, and that is because of the fiber waviness, which causes fiber-fiber contact. So upon elastic longitudinal tension, that is horizontal tension in this picture, the fiber waviness decreases, so the through-thickness resistivity increases. And that's exactly what we see for the through-thickness volume resistance at the bottom here. That resistance indeed increases every time one tensions it in the horizontal direction. Now, damage can occur in aircraft due to bird strike, for instance. And the damage can involve delamination as well as fiber breakage. And we can monitor the fatigue by subjecting the composite to tension-tension fatigue with the tension in the fiber direction and measuring the resistance in the same direction. So at the bottom is what I showed you before, but now I do it for many, many cycles. And we see after 218,000 cycles, the first increase in the baseline resistance. In every cycle, the resistance goes down and up, but then the baseline shifts upward upon damage. And this is fiber breakage, and each breakage involves a fraction of a toe. This is the second fiber breakage occurring a little later. And still later, we see the baseline resistance increasing in every cycle, meaning that fiber breakage occurs in every cycle. And toward the end of the life, the resistance really increases quite abruptly. So we can follow the entire fatigue life of the composite. And shown here, the bottom curve is the resistance down up, right? Is the up, the peak resistance in every cycle. And we see that at about 50% of the fatigue life, the first spurt of resistance increase occurs, meaning that the fiber breakage starts to occur at about 50% of the fatigue life. And the upper curve is the modulus, and indeed the modulus goes down, supporting the fact that there is damage. Next, let's turn to contact resistivity measurement for sensing and interface. In a laminate, you have plies or laminae, and you have interfaces between the plies. And these interlaminar interfaces are mechanical weak links. Any interface is associated with a contact resistance, and so does the interlaminar interface, which is actually a matrix-rich region. With the matrix being insulating, such as the epoxy, the interlaminar interface resistivity is never infinity because of fiber-fiber contact across the interlaminar interface. And delamination decreases the interlaminar fiber touching, thereby increasing the through-thickness interlaminar resistivity. We can measure the interlaminar contact resistivity by using this modified 4-probe method that I devised. I have two plies overlapping, and the overlap region is the interlaminar interface, and I have 4 legs sticking out to accommodate the 4 contacts for the 4-probe method. And so the contact resistivity is the contact resistance times the contact area, which is this overlap area. Another nice thing about this technique is that one can have a 2D array of interlaminar interfaces, and so a 2D array of sensors, thus resulting in 2D spatially resolved sensing. This American airline flight dropped from the sky to New York City, killing over 200 people. And part of the problem is that the tail came off. So it's a fastening problem. Fastening means squeezing or compressing together the 2 components to be joined. And it'd be nice to be able to monitor whether this joint is loosening or not. And this we can do by measuring the contact resistivity. And this is with upon squeezing or compression in the through thickness direction. Every time one compresses, and the compressive stress is shown in the curve below, every time one compresses, the contact resistivity goes down because the squeezing increases the proximity between the plies. However, the resistance decrease is not totally reversible in the case of an epoxy matrix composite. However, for a thermoplastic matrix composite, it's totally reversible. And that is simply because the thermoplastic involves linear molecules, so it's tough relative to the epoxy, which is a thermoset and is brittle, involving cross-linking. So actually, it would be better off if one uses a thermoplastic matrix in place of the epoxy matrix. Composite panels tend to be relatively thin, so measuring the through-thickness resistance is not so convenient. Measuring the in-plane resistance is much more convenient. We can actually measure the in-plane or longitudinal resistance in place of the through-thickness resistance and get similar effects. And this is again that squeezing in the through-thickness direction, and the longitudinal resistance, just like the through-thickness resistance, decreases every time one squeezes. And that is because the through-thickness resistivity decreases due to the enhanced through-thickness fiber proximity, thus promoting the longitudinal current path detour necessitated by the imperfection and thus decreasing the longitudinal resistivity. That is, there's always some little defects in the fibers, and when a defect is encountered, the current path can detour from one fiber to the next across this interface between the fibers. So if there are more fiber-fiber contacts, this detour would be facilitated, thus enhancing the longitudinal resistivity. Damage of aircraft can occur due to impact, such as that by bird or hail. And the contact resistivity is very sensitive to the impact. This shows the contact resistivity upon impact at increasing impact energy, and every time one impacts, the resistivity goes down irreversibly. Even at a tiny impact energy of 0.8 millijoule, we can detect it. The irreversible decrease in that contact resistivity is due to the irreversible increase in the fiber-fiber contact across the interlaminar interface. In addition, this interlaminar interface can serve as a thermistor, that is, a temperature measuring device based on the resistance varying with the temperature. So this is the contact resistivity versus temperature. Upon heating, it decreases because the chance of electrons jumping across the interlaminar interface is enhanced by the heating. Not only detecting the temperature, the contact resistivity responds to the thermal damage of that interface. Here at the bottom shows temperature variation, and upper curve shows the contact resistivity variation. Every time the temperature goes up, the contact resistivity goes down. But at the highest temperature, there's an upward spike in the contact resistivity indicating damage. And if the highest temperature is a little higher, the thermal damage becomes more and the spike becomes more. And this is even more. So we have temperature and thermal damage sensed at the same time. Next, let's turn to surface resistance, which is for sensing a surface region. And the surface resistance is measured by using electrodes or electrical contacts at the surface. So here I have two sending in current from the top. And the current only penetrates to a certain degree. It's incomplete penetration. In spite of that, the surface resistance is very suitable for tracking the flexure. Because under flexure, the tension side and compression side, the two opposite sides, are feeling opposite stresses. One is tension and one is compression. And one can put 4 electrical contacts on each of the two opposite surfaces to measure the top surface resistance and the bottom surface resistance. And this shows the compression surface resistance in bold line. Now, every time one flexes, that compressive surface resistance goes down, and the opposite for the tension side surface resistance. And the reason is this: upon elastic flexure, the tension surface resistance increases due to the fiber waviness decrease, because you are stretching horizontally, so the fiber waviness decreases, and thus the current penetration decreases. And under compression, it's just the opposite. In one scenario, we can have the baseline resistance of the tension side surface resistance climbing up cycle by cycle, and that is due to minor damage. So one can actually see the strain effect and the damage effect simultaneously. Now, if one, instead of measuring the surface resistance, measures the volume resistance, it would not be very wise, because the volume resistance gives you kind of the two opposite effects on the two sides averaged out. So it wouldn't be very suitable at all. Now, there's a big interest in using carbon nanotube in composites. We have looked at the effect of adding carbon nanotube to cement in terms of the piezoresistivity as described by the gauge factor. And you can see that adding carbon nanotube, CNT, to the short carbon fiber, CF, doesn't improve anything. In fact, the gauge factor decreases. The winners are still the carbon fiber, no carbon nanotube at all. The reason for the carbon nanotube not helping that much is their intertwined morphology, making the dispersion of the carbon nanotube not easy. Okay. On the other hand, if you want to modify the interlaminar interface, which is a small region, you need a nanofiller. Okay. So one can put nanotube or other nanofillers such as carbon black here, and that forms a hybrid composite, which is called a hierarchical or multi-scale composite. However, such material modification has disadvantages because of the increased material and processing costs. Also, the applicability to new structures only, not to existing structures, because the existing structures would not have the needed modification. The application of resistance-based self-sensing is good for carbon fiber composites without modification because it's already conductive, but it's not applicable to glass fiber composites unless a conductive filler is present. So that means modification. For sensing matrix cracking, conductive filler incorporation would help. Resistance measurements, though, has limitations. Metals are very low in resistance, so sensitivity would be limited by the need to measure very small changes in the resistance. And also, it's not applicable to polymers or ceramics, which are not conductive. Also, one needs intimate contact between the electrodes and the specimen. So let me now turn to capacitance measurement. The conductivity or resistivity relates to the resistance, but the permittivity is a material property that relates to the capacitance. A conventional conductor does not polarize because there's no electron-atom interaction. The electrons just loop around. But here at the bottom is a case where there is a degree of interaction between a fraction of the electrons and the atoms. As a result, there is polarization. And this makes a conductor a polarizable or dielectric material. And this is a polycrystalline graphite and showing the relative permittivity decreasing a lot with increasing grain size, increasing a lot with decreasing grain size. If one plot versus the 1 over grain size, which relates to the grain boundary area per unit volume, one gets more or less a straight line. And that indicates that the electron-atom interaction occurs at the grain boundaries. Now, dielectric testing involves parallel plate capacitor configuration, and C is the capacitance, kappa is the relative permittivity. But for a conductor, one needs to be careful because an LCR meter is not designed for measuring the capacitance of a conductor. So one needs to put in a thin insulating film between the specimen and an electrode in order to make the LCR meter behave. And one can decouple between the capacitance due to the specimen and the capacitance due to the interface by measuring the capacitance C at 3 or more different thicknesses and plotting 1 over C because this is a matter of capacitors in series, and the slope relates to the permittivity. And so we can decouple between the capacitance due to the specimen and the capacitance due to the interface. Now, poling is not needed for conductors, in contrast to ceramics and polymers, which need poling. And that's because the polarized state of a conductor is inherent due to the space charge polarization occurring at interfaces like grain boundaries. And because of no poling, there's no depoling. Capacitance-based self-sensing is applicable to all dielectric or polarizable materials, regardless of the resistivity. That is beautiful. Both conductors and insulators can be amenable to capacitance-based self-sensing. Piezo permittivity means the effect of strain or stress on the permittivity. And this shows the relative permittivity kappa versus the tensile stress at 3 different stress amplitudes, and the permittivity indeed increases reversibly. This is piezo permittivity. At the bottom is the same material showing the piezo resistivity, with the resistivity increasing quite reversibly upon tension. And the resistivity and permittivity are actually related through the Kramers-Kronig relationship. For cement, the capacitance-based sensing also works. Here we use 2 coplanar electrodes and measure the in-plane capacitance because coplanar electrodes are more amenable to structural implementation for large structures than sandwiching electrodes. And the in-plane capacitance actually decreases upon the normal compression, and that's because of the negative piezo permittivity in this direction. But if one considers the longitudinal or vertical capacitance instead, one sees the capacitance increasing. So this shows the fractional decrease in the capacitance in the transverse direction. The more the normal stress, the more is that decrease. One can also look at damage sensing, and this is the case of continuous carbon fiber polymer matrix composite with artificial damage in the form of tiny little holes making a row in the middle here. And we again use 2 coplanar electrodes on the surface. And so current bows out from the 2 electrodes, and the defects would intersect the electric field lines so that the electric field lines cannot spread so much, and as a result, the capacitance would go down. So the defects cause the capacitance to go down. When the fibers are in this direction, there's more current spreading, and so the sensing is better, with the capacitance going down more for this direction of the fiber than this direction of the fiber. Now, 3D printing needs stress or defect sensing very badly because there are defects, particularly those defects that are between the printed layers and subsurface defects. Those cannot be seen by cameras, and cameras are the conventional methods that people use for sensing defects in 3D printed material. But we can use capacitance-based sensing. The polymer, in this case, is not conductive. And we have 7 dots here, meaning 7 artificially inflicted damage, defects rather, and we have 2 coplanar electrodes on the outer surface. And the defects are positioned between different printed layers. And shown here is the capacitance versus N, which is the number of layers above the defect. Okay? So in general, consider 0 defect to 7 defects for the 7 dots. The more is the defects, the lower is the capacitance, because the defects intersect the electric field lines again, thus decreasing the capacitance. And note that the more is N, the higher is the capacitance, meaning that the sensing is less sensitive. Just because the bigger N means there are more layers above the defect, and the electrodes are at the very top. So the sensitivity for sensing those defects would be less. So we are able to relate the capacitance to both the number of defects and where the defect locates. And we can also do damage sensing or defect sensing for cement using 2 bars. Each is an electrode, but each bar has 9 segments in it, and again, it's coplanar electrodes. And this sample is perfect in this region, and in this square region on the right is defective, having some foamy stuff incorporated in that region during the fabrication. And we measure the capacitance using different numbers of these segments. So A, or 2A and 2A, or 3A and 3A, and so on. And so this is the capacitance versus N of the NA. And the slope relates to the permittivity. And we see that the slope changes. It's a bigger slope for the perfect region and a shallower slope for the defective region, because the permittivity is smaller in the defective region. So we have spatially resolved damage sensing of the cement using capacitance-based self-sensing. Pyropermittivity means the effect of temperature on the permittivity. And this shows the permittivity versus temperature up and down for graphite, and the permittivity increases quite reversibly. And that is because the carrier-atom interaction depends on the temperature. Now I turn to inductance measurement. I've started this inductance research in March of this year, so this is really new. Now, twisting enhances the handleability of fiber tows or yarns. The twist level is the number of twists per inch of the toe, and that's TPI, standing for twist per inch. And the twisted carbon fiber is used for weaving to make fabric. This shows the resistance of the toe decreasing with increasing number of twists. And that decrease of the resistance with twisting is because the number of fiber-fiber contact points is increased by twisting. And this effect causes the inductance to increase. Having more fiber-fiber contact points would enhance the inductance, and that's exactly what we see. And this shows the effects of both tension and twist on the inductance, and the inductance increases upon stress application. This is tensile stress, and the more is the twisting, the more is this effect. So the piezo inductance is enhanced by the twisting, and is not totally reversible, as you can see. Now the resistivity likewise increases upon tension, and the effect is more if one has more twisting. Let's compare these fractional changes in the inductance and resistivity. The twisting here, or the resistivity decrease indicates increase in the number of fiber-fiber contact points in the toe, and twisting increases the number of contact points. However, tension decreases the number of contact points, so the resistivity increases for the tension but decreases for the twisting. Note that the tension effects are much weaker than the twisting effects. Let's compare tension alone versus tension plus twisting. And the tension increases the resistivity regardless of the twisting. Comparing twisting versus twisting with tension, and one sees that twisting plus tension gives less inductance increase than twisting alone. Let's look at the actual inductance values rather than just the fractional changes. Comparing the 12K and 24K fibers at the toes, having more fibers in the toe gives you more inductance. And that makes sense because a larger toe would increase the inductance due to more fiber-fiber contact points. Comparing uncoated carbon fiber versus nickel-coated carbon fiber, the nickel coating increases the inductance, and that's due to the magnetic character of the nickel. The bottom case is that of the uncoated fiber involving two toes that are perpendicular to one another and overlapping to form an interlaminar interface. And this configuration gives by far the highest inductance. And this is that configuration. You have two toes, two laminae, perpendicular to one another and overlapping here, and this is the interlaminar interface, and we have epoxy there. This change in direction alone helps to increase the inductance. Just like the classical inductor coil, in that coil, the current direction keeps changing inside this coil, and that's just Faraday's law. In addition, the interlaminar interface, inside that interface region, you have fiber bending occurring, and that also helps to increase the inductance. And so there are several sources of inductance in composites. The fiber toes themselves, the directional changes of the current path, and the interlaminar interface. So let's extend from this configuration to that of a composite laminate involving two laminae, the fibers in cross-ply configuration. So there are many interlaminar interfaces, and we have the current path shown by these arrows. So the current going like this between the top ply and the bottom ply, and also going through the interlaminar interface. So by having a current path like this, you are really having a lot of inductors in series, and so it's additive in terms of the inductance. And one is not limited to one such current path. There can be many different such current paths maybe parallel to one another for the same two-laminar unit. And we can have multiple two-laminar units in the same laminate. So potentially one can build up the inductance quite a bit. And the inductance means the capacity to make an electromagnet. So we are envisioning structural electromagnet, which is a term that I invented, that is using a structural composite, actually without modification, to be an electromagnet. There are many possible applications of structural electromagnets because magnetic fields are needed for numerous applications, such as motors, generators, transformers, lifting magnets, and magnetic actuation, which means self-actuation. So this is beyond self-sensing. It means an unprecedentedly high level of smartness in structures. And this is just my dream. It's going to be my future work, I hope. So here's the conclusion. Structural self-sensing involving resistance measurement has been studied for decades, but recent work has extended it from resistance measurement to capacitance or inductance measurement. Resistance or inductance measurement is applicable only to conductive materials, such as metals and carbon fiber composites. But capacitance measurement is broadly applicable to conductors and non-conductive materials as long as they are polarizable. The effects of strain, damage, or temperature on the resistivity or permittivity is the basis of the resistance-based or capacitance-based sensing. The effects of fiber-fiber contact, fiber bending, and current direction change on the inductance are the main basis of inductance-based sensing. Thank you.